Okay, guys, so for these first few questions, they're going to be just trying again the ones we did in class, basically with a slightly different situation. But just you can try it again on your own. You can look over your notes. You can pause the video here. We're going to pause the video and then just click continue whenever you're ready, and I'm just going to run through it. So go ahead and try this one. Look to your notes and maybe think for a second about what we need to do here. Drawing a picture first is always your first step. So let's look at this. You have an air freshener that weighs 25 kilograms hanging from a rear view mirror in a car. Sound familiar? It's for a reason. The car is going forward at 3 meters per second squared with an acceleration. What is the angle from the vertical the air freshener hangs? So here was our picture. Again, we had our air freshener. Oops. Just going to draw a little square. Now, even though it's hanging from right here, yeah, this is where like it'd be attached to the rear view mirror. I'm going to draw my triangle coming from the center of the air freshener, but it's going to work out the same way. You should have drawn the force of gravity and then the force of the acceleration of the car. Again, if you have something inside an object that is accelerating, yeah, when we are accelerating, the object feels the force in the opposite direction. Even though it's going forward, we feel the force going the opposite direction. This always works that way. So what you should have done here is realized if it says what is the angle, this means we have to do inverse trig, which means we need to find at least two sides of our triangle. Now I mentioned this in class, but I've had you guys find the force of gravity because I wanted you guys to practice that. Force of gravity, your mass times gravity, always. However, you could draw this triangle using just the acceleration of gravity. We have the force of gravity, which is dependent on your mass. The acceleration of gravity is always 10. Yeah. So we can actually do this question just using 10 because we also have the acceleration. You're going to get pretty much the same answer, yeah. So if you use the forces, great. I wanted you to practice that anyways, but we actually don't even need to know the mass of this object. It's going to be the same thing. Now, because we're finding this angle here, this is going to be tangent, right? Opposite, adjacent. You should have done inverse tangent. Now, again, what you'll see here is I'm going to do this as inverse tangent of 3 divided by 10. We should get the same thing if you had used the forces. So 3 divided by 10, we should have gotten about the same thing, 16.7 degrees is the angle. If you got something close because you used the forces, if you had to round anything off, it should be pretty much the same thing. Once more, if you did, this would have been what? 3 times the mass and 10 times the mass. Again, we'll get the same thing. Let's go ahead and try the next one. So again, draw your picture. This question says, what will be the child's acceleration? I'm going to give you some hints here. If we are trying to solve for acceleration, you need to find the net force in the direction of travel. So that might be a component we have to solve for. Draw your picture, get as far as you can, and if you're not sure, you can press play, and then we'll check from there. Okay, let's see. A child is sliding down a sled on weighing 100 kilograms. The force of friction is negligible, so we're going to ignore friction. That's what that means. The hill has an angle of 5 degrees from the horizontal. What I want you guys to get used to from here is whenever we have these inclines, immediately putting the angle where it needs to go. So I usually draw my axes without arrows so I can keep track of what my vectors are. So there's my axis. Gravity pulls down. There's the force of gravity always. That's what I always start with. And then I next go to where my angle is at. Your angle is always in between the x-axis, the y-axis, and the force of gravity. So I want you guys to get in the habit of when you have these incline questions, immediately putting the angle there where it needs to go. So that's 5 degrees. Okay, now let's think about the direction of this motion. Here's my kid on a sled. I'm just going to draw a box. Think about where the direction of motion is going. He's going down the hill. So the direction of motion is this way. Now, it says that friction is negligible. So that is going to be the net force. There's no friction to fight against. The net force is always the direction of motion. So I just need to find this. Now, what this happens to be is the x component of gravity. Here's gravity pulling down. This right here, I'm going to draw a different color. This right here, I complete the triangle. That is the x component of gravity. Now, again, because my angle is right here, I'm going to find my x component down here instead. But it's the same thing. It's going to be the exact same thing. I just like to find my x component where I have my angle. My angle is here. That's my x component. It's the same. I hope you guys are understanding that this is the same as this. So once we find that force, all we got to do is plug in here and solve. We are ignoring the normal force right now because there's no y movement. So we know that our y net force is going to be 0 because there's no up and down y direction motion. So I'm going to pull off this triangle right here. There's my right angle. I'm going to recopy it tilted so that gravity is my hypotenuse and the 5 degrees is up here. I want to find my x component, and that's this piece right here. That's this piece right here. I need to find my x component of gravity. So we can know the force of gravity because the force of gravity is your mass times gravity. So looking back up, 100 kilograms is this kid on the sled together. So the force of gravity is mass times gravity, 100 times 10. This is going to be 1,000 newtons on my hypotenuse. And then once we know that, all we got to do is trig. This is my opposite. So I'm going to use sine to find it. So my net force is just the x component of gravity. And that's going to be, again, 1,000 newtons times, since this is my opposite, I'm going to be using sine of 5 degrees. So we plug this in the calculator. We should get a force of gravity in the x direction. Wow, not much. Did that right, yeah? Please tell me I'm not in radians. Let me double check. Good, okay, that's interesting. 1,000 sine 5. Yeah, I guess it's a very low hill. Is 87 degrees. Sorry, 87 newtons. Yeah, even though it's 1,000 newtons for gravity, this is a very, very low incline. So this guy's going to be like barely accelerating down the hill. He's like, wee, and it's going to be just barely going. This is a very, very low incline hill. Maybe his parents were kind of scared for him and didn't want him to go down a steep hill. So because we have the force of gravity now, this is the force that he feels pulling down the hill, right? This is why the steeper the hill, the faster you go, because as that angle increases, you're getting closer and closer to directly feeling the 100% effects of gravity. If you're on an incline, you don't feel as much gravity pulling you down unless it gets really steep, and then you feel gravity even more strongly. So the mass, there is our net force. We have a mass of 100. And the acceleration, yep, this poor child, his parents are too overprotective. He's not even going to be accelerating faster than 1 meter per second squared. So he's not going very fast. This is a very, 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 very flat incline. Good. So once again, any questions that say acceleration, find the net force in the direction of travel, then pop in to F equals ma. Let's try another one. Okay, so this is again a now you try. We're looking at the last question. It says from the last question, if the hill has a friction force of 45 newtons, how fast will a child be accelerating now? So once again, any acceleration questions, you need to find the net force in the direction of travel. So here's how this picture is different. Actually, I'm sorry, I lied. I want you guys to go ahead and try it. Okay, let's take a look. So draw, here's how our picture is different. Okay. Here's my axis. Here's gravity. That's still the same. We have the force of gravity in the x direction we already found as being 87 newtons. But they are fighting now against some friction in this direction of 45 newtons. So now the net force is going to be a bit less. Yeah, they have to fight against some friction. So this is what I messed up on in class. Because we're traveling in this direction, I'm going to call this one positive because that's the direction of travel, and I'm going to call this one negative because it's opposite to the direction of travel. So that's 87. Sorry, that's from the last one. So our net force is 87 newtons in the positive direction minus 45 newtons in the other direction. Our net force is 42 newtons. So this poor kid is going to go even slower if there's friction. So now we plug in our net force is 42 newtons. The mass is still 100 kilograms from that kid. And we're trying to find how fast he's going to go now. Yep, he's going to go even slower, this poor kid. This is an acceleration of 0.42 meters per second squared. Again, we were finding the net force in the direction of motion, and we already found that the x component of gravity would be 87. So that's why I didn't need to redo this whole question. I already found it was 87 in that direction, fighting against a friction of 45. Okay, this is another now you try. So this is the elevator question. Remember, if you are an object in something that is moving, whatever direction the object is moving, you feel the force in the opposite direction because you are resisting that motion. An object at rest tends to stay at rest. I'm plugging in my laptop here. An object at rest tends to stay at rest. So if you are in an object that is moving, you feel the force in the opposite direction because you are resisting that motion. So go ahead and take a look at your notes. Try these two questions and we'll come back in just a sec while I plug in my laptop. I'm not even going to pause the video yet. Okay, there we go. Okay, now I'll pause the video and then you can come back when you're ready. Okay, so again, for A, the elevator is moving upward in this case. We got a kid on a scale that weighs 50 kilograms, and the elevator is moving upward with an acceleration of 0.45. So again, we have two forces acting on this person, acting on the scale, I should say. We have the downward force of gravity, and we have the downward force of the acceleration of the elevator. The elevator is moving up, but you want to stay put, and so you feel the force in the opposite direction. So the weight on the scale in newtons is going to be these two forces added together. F equals ma. The force of gravity on you, you're 50 kilograms, times the force of gravity is 10 meters per second squared. That's 50 kilograms times 10 meters per second squared. Comes out to be 500 newtons. The force from the acceleration of the elevator, I'm sorry, I just realized the stuff was covering you up, is your mass times the acceleration of the elevator. So 50 times the elevator was 0.75. We got 37.5 newtons. So the reading on the scale is actually going to be these two things added together. 500 newtons from just your normal weight in newtons, plus that additional weight it's going to feel from the acceleration of the elevator. The scale will read a little bit more and think you are heavier than you actually are. Now for B, we have the opposite situation. When the elevator is going downward, you feel the force in the opposite direction because you're resisting that motion. So now our vectors are going to point in different directions. Now we still have the force of gravity. which again we found to be 500 newtons. The force of the acceleration now is going to be pointing upwards. So when we have vectors that point in different directions, we're going to have to subtract them. So we have 2 meters per second squared is the acceleration. Mass times acceleration, 50 times 2 gives us 100 newtons pointing upwards. So you have 100 newtons pointing upwards, 500 newtons pointing downwards. What the scale is going to read is the net of those. So 500 minus 100. The scale is going to read 400 newtons. Hopefully that makes a little bit of sense. Again, if you want to, if you have access to an elevator, take a scale in there and try this. You'll see how it works. Okay, we got a few questions left. Now these last few ones here that we're going to be doing, I'm going to walk through one with you, and then you are going to try it next, because these ones we didn't get to in class. So let's go ahead and try this. You pull 2 blocks connected by a lightweight string across a horizontal table. 2 blocks connected by a string, and then you're pulling on one of them. Block 1 has a mass of 1 kilogram, and block 2 has a mass of 2 kilograms. I'm going to go ahead and, just because this is to the right, always makes more sense in my mind, I'm going to call this block 1 and this block 2. And I'm going to be pulling it on this direction. There's negligible friction between the blocks in the table. Okay, ignore friction. The string will break if the tension is greater than 6 newtons. We're trying to figure out what's the most force we can pull on block 1 without breaking the string. So here's how we break this down. What's going to happen here is, again, the maximum force that this string can feel is 6 newtons. So we know to start with that this force right here, this is going to be called the force tension, is going to be 6 newtons right here. We need to pull with enough force on this end to get both of these blocks moving, but to not break the string. Now again, if I feel a force tension going this direction, 6 newtons, that means block 2 is only going to feel that force. Block 1 is going to have the total force acting on it, but block 2 is only going to feel the force right here from this string. So the force acting on block 2 is just 6 newtons. What's going to happen out here, my total force total, that I'm going to be applying to block 1 needs to be this 6 newtons, or at max can be that 6 newtons, plus the force that I need to pull block 1. This is the force I need to pull block 2. I need to know what's the force that I'm going to be pulling block 1 at. So I'm going to call this force 1. So here's what we're finding. Again, this is the force to pull block 2 plus the force to pull block 1. Well, here's what we need to know. We need to know how fast this is going, right? Force is mass times acceleration. In order to find a force, well, I know the masses, but I don't know the acceleration. However, if we look over here, what we're going to do is we're going to separate our system into these 2 objects. They are going to, hopefully you guys can understand, if I'm pulling on block 1 and these 2 blocks are connected, they're going to have the same acceleration, right? They move together. They're a system. So I know the force that block 2 is going to be pulled on at. The force of the string is what will pull block 2. Now, block 2 has a mass of 2 kilograms, so we can find how fast it's going. It's going to have an acceleration of 3 meters per second squared. Now, again, if block 2 is moving with that acceleration, block 1 also has to move with that same acceleration because they're moving together. So I'm going to be able to find this force right here, and then I'll be able to say the total force that I will be applying in order to get both of these blocks moving and not break the string. So the force that I feel on block 1 is its mass, which is again 1 kilogram, times the acceleration of the system, which we just found to be 3. So the force that block 1 is going to feel is 3 newtons. So, or at least what I need to pull it, I'll say that. So the total force we are applying to block 1 is, once more, the force to pull just block 1 at that acceleration plus the force to pull block 2, which was the 6 newtons. So the total force is going to be 6 plus 3 newtons. It'll be 9 newtons that will be applied here on block 1. 3 newtons to get just block 1 moving, plus the 6 newtons to get block 2 moving. That's going to be our answer. So this little formula right here is going to be key for the next question. Your total force is going to equal the 2 forces individually of the blocks added together. 6 newtons here, 3 newtons here is what we found. Keep this in mind. Total force, force of block 1 plus force of block 2. So try this one now. Say you pull on block 1 such that they are accelerating together at 1.5 meters per second squared. So we are now given the acceleration. You want to find 2 things. What's the force of tension in the string? Now, the force of tension in the string is the force pulling block 2. Keep that in mind. As well as the total force we're using on block 1. So again, here's what we had. Force total equals force of block, sorry guys. I accidentally touched the corners and that happens. Force of block 1 plus force of block 2. Stop doing that. Which is the force of block 1 plus the force tension. The force tension is the force that the block 2 is going to feel. So go ahead and try this one. Okay, let's look at this. So here's my picture again. Block 1, block 2. I'm going to look at these separately. I'm going to find again the forces of in the string is going to be the force required to pull block 2. Force of tension is going to be for block 2. And this is going to be actually pretty easy because we know the mass and we are given the acceleration now. So we just got to plug in. So force equals the mass of block 2 was 2. If you look back to the question, the acceleration is now 1.5. So now this force tension, or again for block 2, is going to be 3 newtons. So that's our first answer. The force required to pull block 2 is the force of tension in the string. Okay, man, this is bad. There we go. Okay, now in order to find the total force that we're pulling on block 1 with, we need to add together the force of just block 2 plus the force of if I only needed to pull block 1. So block 1 has a mass of 1, still an acceleration of 1.5. Again, I was told the acceleration here. The force of block 1 is 1.5. So these 2 things added together, this is the answer to our first question. The total force is the force to pull block 2 plus, the force to pull block 1, 4.5 newtons. So again, 4.5 newtons is acting on block 1 because we're pulling from there. But when we're trying to find the total force, we actually look at these as separate objects. How much force if I was just pulling block 2? How much force would I need? If I was just pulling block 1, how much force do I need? Add those together, and that's what you actually have to apply to block 1 in order to get both of them moving. Okay, we have one last question we're going to do. So again, we're going to try this one, and then you guys are going to try one on your own. So a 60-kilogram skier starts from rest at the top of a hill with a 30-degree slope. So let's go ahead and draw this picture. Get used to this. Force of gravity gets drawn first. Put your angle on the picture in between force of gravity and the y-axis. I want you guys to get in the habit of whenever there's an incline question, immediately going to this setup. XY axis, force of gravity, angle. Always start there. She reaches the bottom of the slope 4 seconds later. Ooh, this is going to give us a hint. We got to combine some information here. There is a constant 72-degree friction force that resists her motion. I'm going to go ahead and draw that as well. 72 newtons, I think I said degrees, sorry. How long is the hill? Ooh, so we're going to kind of work our way backwards from this, guys. If they are asking how long the hill is, that's going back to our kinematics. How long the hill is, what is the distance traveled? And hey, look, we have time. So since we have time and we're trying to find distance traveled, here's our end goal. Our end goal is the position formula. We have time. We're looking for how far down the hill she's gone, how long the hill is. We need to use position formula. So let's look at this formula here, and then we'll kind of attack this. Now, we want to find x final. We know t, we know it's 4 seconds later. We know that she starts from rest at the top of the hill. We are going to be able to ignore this part of the equation. If you start from rest, you have an initial velocity of 0. If they don't tell you an initial starting position, we ignore xi. This is the only part of the formula we need. And so what we need to know is the acceleration. So we're going to find acceleration like normal. We're going to find the net force in the direction of travel, and then solve for acceleration. So I kind of want you guys to try this one on your own first. I'm going to give you one more little hint here. Remember, the direction of travel is down the slope. This is the force of friction. Down the slope, you should know which component of gravity that is. That's the x component of gravity. Solve for it down here. My angle is right here. So let's solve for the x component down here. Find the net force. I've got force of gravity x, I've got force of friction. Solve for acceleration and see if you can keep going. Okay, let's check. So I'm going to find the x direction of gravity, because in order to find the net force, I've got these two forces acting against each other. I need to know the x direction. So let's pull off our triangle. Here's my right angle. I've got force of gravity is my hypotenuse. I've got 30 degrees. I'm trying to find the x component. So force of gravity, your mass times gravity. The mass is 60 kilograms. So force of gravity here. I'm going to move this out of the way. Nope, I can't do that. That's okay. Excuse me. Force of gravity is your mass times gravity. So 60 times 10. 600 newtons is on the hypotenuse. Once again, the x component in this case, it's not always this case, but the x component is the opposite. So always it ends up being the magnitude of the hypotenuse times the trig function, in this case sine, of 30. So the x component is 300. So let's go back up to our picture. I have an x component here of 300 newtons fighting against a friction of 72 newtons. My net force is going to be those subtracted. 300 minus 72, which is 228. Yeah. This is my net force. Now we can find the acceleration. I'm going to work my way backwards. Now that we know the net force, let's work our way back up. I can find the acceleration. Remember, our end goal is to find how long the hill is. But I'm going to find the acceleration first, and then I'm going to plug back into that original formula. I'm working my way back up. Working my way back to you, babe. The mass is 60 kilograms times the acceleration. This is F equals ma, guys. Sorry about that. There we go. Divide by 60. We get an acceleration of 3.8. Anytime you guys do a question, you always go, okay, I'm done. Wait, let me go back. Let me read the question. I found acceleration. I want to know how long the hill is. So we're going to plug back into our original goal here. 1/2, the acceleration was 3.8. The time they gave us just happens to be 4 seconds. 4 squared. So we get this hill is 30.4 meters. So again, guys, you always want to try and work back in these problems. You start with your end goal. We started here with our end goal of, I want to know the distance traveled. And then we ask ourselves, do I have all the information? Oh, no, I don't. I need acceleration. How do I find acceleration? F equals ma. Okay, I need the net force. And then once you reach the base level, then you can work your way back up. So you're going to try this one more time. This is the last question. This is going to be similar in that we are going to use a kinematic equation. However, this question says the hill is 200 meters long. So I'm giving you x final. We are solving for t. That's the only difference. And because we're starting from rest again, guys, you're only going to be looking at x final equals 1/2 at squared. You're not going to have to do quadratic formula or anything like that. Go ahead and try this one. Okay, so this guy here, again, get used to drawing your picture. X axis. Oh, I didn't want purple this time. X and Y axis, force of gravity. Get used to that. And angle is set 25. Get used to that's always your original picture. Okay, now there's a force of friction of 50 newtons going back this way. So let me actually, now I'm going to try some purple. Force of friction is 50 newtons. We need to know the x component of gravity in order to get our net force. So once again, here's our end goal. I know x final. We're trying to find time. I need acceleration. In order to get acceleration, I need to know the net force and the direction of travel. So I need to find this x component, which I'm going to solve for down here. So you pull off your triangle. 25 degrees is up top. Force of gravity is right here. Your mass times gravity. 70 kilograms times gravity. 70 times 10. 700 newtons. And here's my x component. Once again, x component is opposite. 700 times sine 25. The x component of gravity in this case is going to be 295.8. Sure, why not? I lied. I'm going to round up to 6. I'm wishy-washy with how I round things. 296 newtons headed in this direction. So our net force is those subtracted. 296 minus 50. We have a net force of 246 newtons. Then we can go back up and solve for acceleration. Trying to keep this as organized as possible. Let's solve for acceleration here. If this is my net force, I'm going to go ahead and actually just do that right here. F equals ma. Our F is 246. Our mass is 70. Let's solve for the acceleration of this skier or snowboarder. 246 divided by 70. We should get an acceleration. Trying to keep this all straight. An acceleration of 3.5 meters per second squared. So let's go up. We are now going to plug in here. Our x final is 200. X final is 200. Acceleration we found is 3.5. We're going to solve for t. So I'm just going to go through and solve this whole thing because I'm running out of space here and I did not plan this out quite right. Let's see. 0.5. Take the square root. We should have gotten a t of about 10.7 seconds. Okay, so I really hope this is making more sense. I know I made some mistakes on Friday, but again, these questions all really work the same way. We're trying to find the net force is always where we start. We think, what's the direction of travel? Do I have any forces that I'm acting against? Do I have multiple forces going in the same direction and I need to add them together? And that is the difference here. Here, we had forces acting against each other. In the block question, we had forces going in the same direction, so we added them. Really, if we can do a good job of keeping these things straight, it'll start getting easier. We're going to continue to practice this on Monday. Let me know if you guys have any additional questions.